Assalamualaikum. My name is Hafizatul Zakia binti Muhammad Fazil. My number matric is 16 DET 19F 2017, class DET4A, and my supervisor name is Puan Salma binti Nisa Atamadin. For this mini project, the objective is schematic capture print, function component, PCB layout print, 3D visualizer, how to etching, how to solder, and how to testing. Also have the video etching, soldering, and testing. First, this is my schematic capture. This is schematic capture print. The function of component IN4007 diode belongs to the silicon family of IN400 series. It is a general purpose rectifying diode that serves its purpose of converting alternating current signal AC to direct current signal DC in electronic product. Second, 2N2222. The 2N2222 is a common NPN bipolar junction transistor BJT used for general purpose low power amplifying or switching application. It is designed for low to medium current, low power, medium voltage, and can operate at moderately high speeds. 7805 IC 7805 is a 5 voltage regulator that restricts the output voltage to 5 volt output for various range of input voltage. It acts as an excellent component against input voltage fluctuation for circuit and adds an additional safety to your circuitry. It is inexpensive, easily available, and very much commonly used. 7812 IC. The IC 7812 is a positive voltage regulator, which means that it generates the positive voltage with respect to the common ground. In case if both of the positive and negative voltage supply is needed in the same circuit, the voltage regulator is IC 7812 is combined with its corresponding 79XX family IC, that is 7912 IC. Then capacitor. Capacitor is an electronic component that stores and releases electricity in a circuit. It also passes alternating current without passing direct current. A capacitor is an indispensable part of electronic equipment and is thus almost invariably used in an electronic circuit. LED green and red. LED, in the simplest term, a light emitting diode. LED is a semiconductor device that emits light when an electric current is passed through it. Light is produced when the particles that carry the current, known as electrons and holes, combine together within the semiconductor material. Logic state. Logic state, the logical stance, true or false, of a given binary signal. A binary signal is a digital signal that has only two valid values. In physical terms, the logical sense of a binary signal is determined by the voltage level or current value of the signal, and this in turn is determined by the device technology. Transformer. A transformer is an electrical device that treats voltage for current in a circuit while not affecting the total electrical power. This means it takes high voltage electricity with a small current and changes it into low voltage electricity with a large current, or vice versa. NTA R4612 relay are switches that open and close circuit electromechanically or electronically. Relay control one electrical circuit by opening and closing contacts in another circuit. RES, a resistor, is a passive two-terminal electrical component that implements electrical resistance as a circuit element. In electronic circuit, resistors are used to reduce current flow, adjust signal level to divide voltage, bias active element, and terminate transmission line, among other use. SIL 10002 seal socket are commonly used in circuit board with short LED pin, like servers or desktop computer. They are typically found in PCB with memory modules and are used in smaller applications like resistor arrays and diode. The socket can also be used in a large component like oscillator and timer. TB block 1 I2 and TB block I3. The MSD series of terminal block is characterized by its particularly small dimension and is the ideal for use in PCB for the transmission of signal and or for low voltage and limited current intensity, particularly when it is necessary to wire a large number of contacts in a small space. VSign and trans to P2S its function for to simulate the circuit. This is my PCB layout and this is my PCB layout print. This is my 3D visualizer. This is at the back. How to etching. Step 1. First, you need to design the board using a service like Eagle Freezing, or you can even just use Adobe Illustrator if you know exactly what you want. And remember to flip the design once you have it complete before you print it. Step 2. Print out the design onto the shiny side of the transfer paper. Step 3. Sand the copper plate so there is a rough surface for the design to stick to when transferred. Step 4. Wash the copper with some water and rubbing alcohol and let it dry. Step 5. Cut out the design and place them face down on the copper. Step 6. Run the copper plate with the design face down through a laminator 5 to 7 times until the plate is hot. Step 7. After running the plate through a laminator or iron, place the plate into a cold batch and agitate until the paper floats off. Step 8. Place the PCB into the etching solution and agitate for 25 until 30 minutes or until all the copper has dissolved around the design. Step 9. Once all the copper is gone, rinse it in the water bed, let it dry and use rubbing alcohol to wipe off the ink transfer onto the PCB. Step 10. Now you have a etched PCB board, but you still need to drill the holes. How to solder? First, mount the component. Begin by inserting the leads of the component into the holes of the circuit board. Flip the board over and bend the leads outward at 45 angle. This will help the component make a better connection with the copper pad and prevent it from falling out while soldering. Step 2. Heat the joint. Turn your soldering iron on and if it has an adjustable heat control, set it to 400 °C. At this point, touch the tip of the iron to the copper pad and the resistor lead at the same time. You need to hold the soldering iron in place for 3 until 4 seconds in order to hit the pad and the lead. Step 3. Apply solder to joint. Continue holding the soldering iron on the copper pad and the lead and touch your solder to the joint. Important, don't touch the solder directly to the tip of the iron. You want the joint to be hot enough to melt the solder when it's touched. If the joint is too cold, it will form a bad connection. Step 4. Snip the leads. Remove the soldering iron and let the solder cool down naturally. Don't blow on the solder as this will cause a bad joint. Once cool, you can snip the extra wire from leads. How to test? Step 1. Design review. You are probably past this step. Verify that the design meets your requirement. Will do what you need. Verify that the FPGA pins are assigned in a way that will satisfy the FPGA design's need. Verify external interface connectors are designed correctly. Analyze trace for signal integrity. Analysis part selection and perform worst case analysis on all components. Step 2. FPGA testing. I recommend verifying for FPGA design first by simulation, but I know many people will skip this step. You can also try to verify the full design or part of it using a development kit, or you can both. Step 3. Receiving inspection. After the PCB returns from fabrication, inspect it to ensure that all parts are placed properly and in the correct orientation. Verify good workmanship on solder joint. Step 4. Save to make. Select critical area of your card to test isolation, resistance, and continuity. Essentially, pick some place where you can measure resistance using a multimeter, estimate what the expected resistance should be, then measure and compare. This will help find any defect, especially those that could do damage when power is applied. Step 5. Power up test. Configure your card in the safest state possible. This means don't install ICs that are removable unless they are necessary. Don't connect interface that don't need to be connected. Current limit your power supply. Use a less than nominal supply voltage. Power up your card and measure voltage regulator output and any other supply voltage or bias current that are important to correct operation. You can also check that your oscillator is function or any other basic function of your board here. Step 6. Functional testing. Design some tests to verify basic functionality. These are very application specific, so I won't go into much detail here. You generally want to make sure that your interface works correctly and make sure your card performs all of its key function under nominal condition. Most of your remaining bugs issues should be resolved by the end of this step. Step 7. Calibration. This is where you calibrate any measurement that are being made by the device. This may not always apply and will be very application specific. By this stage, you should be very precise about how you are making and documenting your measurements. Step 8. Performance testing. This is where you will identify key performance criteria and measure what performance you are achieving. Example may include SNR, bandwidth, latency, power consumption, data rate. Step 9. Environmental testing. This is where you verify that your design will function in the environment it was designed for. This often include thermal cycling but may also include vacuum testing, submersion, radiation testing. You will often repeat functional calibration and or performance tests in each environment that the card may be subjected to. Okay, this is the video for teaching.
Onto the copper board, I use magazine paper, just local supermarket magazine. Pages are glossy. The only thing it'll transfer onto the copper board from when you print on this is the actual toner, so it's ideal. So we'll go ahead and place one of these over this image so we know it's going to print in the right place. So do the same for the silkscreen layer. Copper board up, get all dirt off, make sure it's nice and shiny. I just use a scotch pad And then it's putting this face down over that image. Make sure it lines up. This board's a bit smaller than what I need, but it's just enough cut I've got for this video. It goes in there. And that round. I'm just using masking tape. Tape. That's it. Be transferred. Transfer the image onto the copper board is this nail varnish remover or nail polish remover. It works absolutely fine. I used to use it on silkscreen layer and just decided to give it a go on the copper board layer to save all the time of ironing and heat transfer. And it works. So let's give it a go. Make sure it's all spread out and then rub fairly hard across all the area. If you don't apply enough pressure, then it may not transfer correctly on. I've done this a few times and not applied enough pressure. There you go, and you feel it's on to dry, and at that point I stop then. Just let it dry a bit. Transferred off the magazine paper straight into the cupboard. Now when it starts drying you will get a bit of white tinge, and that's just a few fibres of the magazine paper. All I do is just a damp sponge like so, ready for etching. Using ferric chloride, ready mixed. I haven't had a problem with this. I know there's other ones out there, people make their own, which I wouldn't mind having a go of at some point, but that works for me. Just put in a small dish. There's the board. Nice, pop it in. But it's fully etched now. So just rinse it in water. On to the next stage. Using no heat transfer method. Let's do the silk screen layer now on the reverse. So all I've done, on double-sided boards, I've never had a problem, to be honest. Time the copper's etched away, it's been a rough fibre board. But on single-sided boards, I've had to just roughen it up slightly with a bit of wire wool, just give it a bit of a key, to be honest. So let's place that in there.
Okay, this is the same like the first one. We will see for the soldering.
This video shows basic soldering technique and the equipment used to solder. There are two main types of soldering iron. The iron to the right has a station which shows the temperature on the display. The controls adjust the desired target temperature. The one on the left works at a fixed temperature but is used in the same way. If you're using a digital iron, then set the target temperature to around 350 degrees C and wait for the iron to heat up. When you're not soldering, remember to keep the iron in the holder. Be careful when you're soldering not to put the iron in contact with the lead. Some soldering irons have PVC coated leads which will melt through easily and pose a risk of electric shock if touched. The best leads to use are made from silicon, which won't melt at the temperatures soldering irons reach. The other item you'll need is of course solder. Solder is a low melting point alloy which flows easily when heated to its liquid state. When it cools and solidifies, it fuses to the surface of a metal at the molecular level, providing good electrical conductivity between two metal surfaces. Solder normally contains flux, which helps the solder to flow, and also helps make a good contact by removing the oxides on the surface of the metals being joined. Although modern flux is not toxic, when soldering you should always use a fume extractor to prevent the fumes from the flux irritating your lungs. The fumes are extracted by a high-efficiency particulate air filter, or HEPA filter, before the air is returned to the room. Before you handle the components, it's strongly advised that you wear an earthing band to prevent electrostatic damage to the components. There are two different soldering types, surface mount and through-hole. Surface mount connections are made by heating components with pre-applied solder in an oven so that it melts and joins to the surface of the board. For this tutorial, we'll look at plated through-hole soldering, which is done on boards with printed circuits on both sides. Through-hole soldering is when components are pushed through a hole in the board and soldered from the other side. The solder flows through the hole to make the best possible contact. First, take your component and create a bend in the legs with a pair of pliers, so that each leg is at a right angle. Push the legs through the holes in the board at the appropriate place and push it all the way down. Then turn the board over and bend the legs slightly to lock the component in place. When the iron is up to temperature, first clean the tip of the iron on the wet sponge on the iron holder to remove any excess solder and flux residue that might be there. You then apply heat directly to the pad for about a second, before placing the solder in contact with the pad. When the solder starts to melt, feed it in for about a second. Take the solder away, but leave the iron on the pad for another second. Then take the iron away and let the connection cool. Let's have another look at that. Before you make another connection, it's important to remove any excess solder remaining on the tip of the iron. This is because any flux in the solder will vaporize until there's none remaining. If you try to make a connection with solder without any flux in it, you risk making a bad connection. When you turn the board over, you should see that the solder has flowed through the hole by capillary action, guaranteeing a good contact. Trim the leads just above the solder using some wire cutters. When you cut the wires, be careful that the cut end is held captive so that it doesn't fly off. This can be done by putting your finger on the end when cutting. If you make a bad joint or want to remove a component, you can remove the solder by using a desoldering pump. This is a spring-loaded piston with a trigger which when released creates a vacuum which sucks the solder up. Cock the pump. Use the iron to melt the connection and put the tip of the pump onto the melted solder, then release the trigger. You might have to repeat the operation several times to clear all of the solder. An ideal solder should look like a cone with slightly concave sides, showing that the solder has flowed through the hole. You can see all the solders here look regular. Bad joints are noticeably different to the concave cones of good joints. If your joint looks like any of these, then it'd be wise to remake it. Bad joints can lead to intermittent connections or no connection at all.
We will see how to testing.
Welcome to GTD. Today I will be showing you what continuity is and how to test for it using a multimeter. Continuity is present when 2 points in an electrical pathway have a connection. This connection must be continuous without any break or open in the circuit. Checking for continuity is extremely beneficial in verifying circuits, finding breaks in wires, checking solder joints, and confirming inputs and outputs. Using a multimeter, I can check to see if connections are linked together with a continuity test function. This is represented by a sound wave symbol on the multimeter's dial. I will be using a few different applications to show what could be expected in a typical continuity test. Make sure that the application being tested is removed from any power before testing. I will use this clean circuit board for my first test. Since this is a new circuit board, the electrical pathways can be clearly seen and followed. A circuit board that has been soldered will not be as easy to identify pathways. I will turn on my multimeter to the desired test function and check to see if it is in working condition by touching the two leads together. Most multimeters will beep when touched together. The value on the multimeter will either show a 0 or a low value. This is because some multimeters will be checking for voltage or resistance when testing for continuity. I can now place the probe on 2 connection points and I should hear a beep. I will do this again, but on 2 parts that are not electrically connected. There is no beep and the meter indicates an OL. Now I will use a cable with color-coded conductors to show how the meter can check for continuity. As you can see, the blue wire on each end has continuity when tested. I will now use a different cable that has the same color conductors. I can use one test probe on a wire and then use the other test probe on each wire on the other end to find the appropriate connection. This can help trace back unlabeled wires or to verify connections from one device to another. Multimeters, along with thousands of other products and services, are available at gelco.com.
Okay, this is my schematic capture. When the logistic is 0, the LED red will be shown, and when the logistic is 1, the LED green is shown with the LED red. This is my PCB layout, and this is my 3D visualizer.